Alright, we're going to do section 3.5, equation solving and modeling. In this section, we're going to use the properties of logarithms that we learned in the two previous sections to try to solve equations involving exponential and logarithmic expressions. And there can be more than one way to approach these problems, and so we're going to work out quite a few so that you can kind of see the general strategy that you should take. So in example 1, it says find the exact solution algebraically and check it by substituting it into the original equation. So here we have 36 times this exponential expression, 1/3 to the x over 5 equals 4. The first thing I want to do is get the exponential expression by itself. So I'm going to divide by 36 on both sides. So this is going to give me 1/3 x over 5 to the x over 5 equals 4 over 36 reduces to 1 over 9. Now it's really helpful for me to continue to write this 1 over 9 as a fraction because can you think of a relationship between 1/3 and 1/9, something that we could do there? Isn't it true that we can rewrite x to the, or we can rewrite 1 over 9 as 1/3 to some power? And what power would that be? Well, we can square 1/3, and that would give us 1 squared over 3 squared, which is 1 over 9. And so there's a property where if I have 1/3 to some power equals 1/3 to some power, because those bases of those expressions are the same, we can just take the exponents and set them equal to each other. So x over 5 would equal 2, because that's what our two exponents over here are. X over 5, 2. And then we just would solve this by timesing by 5 on both sides. So x equals 10. That's our answer on this. And then it is asking us to plug this in to our original equation to check to make sure we did it right. So that won't take too long. I'm going to plug it in on the left side here. And I'm going to work with the left side until I end up with what the right side is. Okay, so if I just plug 10 in, this is what I have. So the first thing I would do here is I would multiply in my exponent, or not multiply, divide. 10 divided by 5 is 2. Then I would say, well, I know what 1/3 squared is. 1/3 squared happens to be 1/9. And 36 times 1/9 is 4, which is what we were trying to get. So we are right that x equals 10. Example 2, again, we're finding the solutions algebraically and checking back into the equation to make sure we did it right. So in this one, we have, again, a number times our exponential expression here, 4 to the x over 2, equaling another number. So we're going to start the same way by dividing by 3. So 4 to the x over 2 equals 96 divided by 3 is 32. From here we can take two different approaches. We can actually write both sides of this as 2 to some power. So 4 is really 2 squared, and so that gives us like 2 squared to the x over 2 power. 32 is 2 to the 5th power. If you don't have that memorized, you just do a little finger math or whatever, and or calculator math and figure that out. Now what happens here, if I have 2 squared to the x over 2 power, I multiply those exponents together. So I'm going to say 2 times x over 2, which 2 over 1 times x over 2, that's what's happening in the exponent. Oh look, that's just x. So 2 to the x equals 2 to the 5th. By that same property that we used last time, we have 2 to some power equals 2 to some power, so those have to be equal. So x should equal 5. The other way that we could have done it is right here, if we maybe didn't realize that we could write these both as 2 to some power, we can use natural logarithms or regular logarithms, well, like common logarithms, whatever we want to. We take the log of each side of this and work with it that way. And to do that, you're going to end up using your calculator. You'd move this x over 2 in front, and end up dividing by log of 4 over here. Another thing you could do is you could take this and write it as a logarithmic expression. This first thing that we had, we could say that this is log with a base of 4 of 32 equals x over 2. And we're going to end up with the same thing we would have ended up down here with log of 32 over log of 4. And then you'd multiply that answer by 2. So that, see how there's multiple ways there to do it. I personally think the first way is the coolest, but you know, you don't have to take my word for it. If I want to plug this in to check, I'd do 3 times 4 to the 5 halves, and 4 to the 5 halves. Well, you're taking the square root of 4. That's what the half power is. That's a 2. And then 2 to the 5th power is 32. So that's 3 times 32, which is in fact 96. Or if you were stumped by the whole 5 halves things and wanted to type that in on the calculator, I suppose you could. Example 3. Now, this time we have a logarithm, and a lot of times when they start off giving us a logarithm, the most helpful thing to do is to switch it to an exponential equation. So we start with this base when we go around, and this is our exponent, and then it equals this. It goes in a circle. And so 4 to the first power is just 4, so let's subtract 1 from each side. Gives me 3 equals negative x, which means x equals negative 3, because I divide each side by a negative. So x equals negative 3. Now, whenever I go back and plug this in, we're most likely going to want to use our calculator here. We can go ahead and simplify it a little bit and say this is log of, with a base of 4 of, that's really 1 plus 3, which is 4. Oh, wait, we don't need our calculator. If the base is the same as this, log base 4 of 4, well, that's just 1 because the numbers match. So, yes, we did that right. Hooray for us. I didn't mean to erase that quite so much. 1 check mark. Yay. We're going to continue solving our equations algebraically, but we may end up with decimals here. And it tells us to obtain a numerical approximation for our solution and check it by substituting into the original equation. So just kind of what we've been doing already. So, I mean, we could take a logarithm on each side here and solve, or we could rewrite this as a logarithm. Normally, if it's in an exponential equation, you're going to somehow have to use a logarithm, switch it to a logarithm, or not necessarily have to use it, but that's going to be one way to do it. So if I rewrite this as a logarithm, I get log with a base of 1.06 of 4.1 equals x. Well, we can type that into our calculator. If you have an older calculator, you would use the change of base formula, which is what I'm doing right now. If you have a newer one and it lets you plug in your logarithms all pretty like, then have at it. I'm typing this in on my calculator so I can figure out that this is something like 24.215. That's our answer. Now when we check this in our original thing, I still have that up on my calculator, and you should too. So we're going to put in 24.215 here, but I'm actually going to do 1.06 to and then I'm going to put second answer so that I didn't have to round at all. That gives me 4.1. If I didn't do second answer, I wonder what it would give me. 1.06 to the 24.215. It gives me 4.099997801, which is really close to 4.1, probably close enough that you would be able to tell, okay, I did it right, but as long as we have the second answer key, we might as well use it. example 5, we want to start off by, let's get this e by itself. When we have e in an equation, there's something we can do that's a little cooler. We can use natural logs, which a lot of times, I don't know, it seems like it works out more nicer. Anyway, 2 minus 7 here is negative 5. Let's divide by negative 3. And that gives us e to the negative x equals a negative and a negative cancel and give us 5/3. Now, the neat thing we can do here is we can take the natural log of each side. And the reason why that is neat is because natural log and e are friends, and when they get together, they go away. So that this is just negative x equals the natural log of 5/3, or I could say that's positive x equals negative natural log of 5/3, and then we do want to go ahead and figure out what the decimal approximation of that is. So I'm going to type in negative natural log 5 divided by 3, and I get negative 0.511 for my answer. And then I'm going to go back and check it. So this is one where it'd be really easy, probably easier to type in the calculator. Sometimes it's not, depending on your opinion, it's not necessarily easier to type into your calculator because it's pretty easy to work through it, algebraically. But this is one where I personally would want to just type it in. 7 minus 3 times e to the negative second answer. Notice that negative was in there originally, but our answer is also negative that we got. So you want to make sure to put negative answer or you're going to get the wrong thing. If you put this in right, you do get 2. If you don't believe me, try it for yourself. So we really did get the right answer on that. Example 6 and 7. We're going to look at the domain of two functions, and on the actual problems that are in the section, you're also going to then match the function with its graph, and we're going to use the domain to do that. So, and you can graph them on your calculator and compare, because these are a little bit tougher than just trying to transform something. And what they want us to get at has to do with what numbers are we allowed to plug in for a logarithm. So remember, we did some problems where we ended up basically trying to plug in like log of, negative 3 or something like that. And if you try to plug that in, you get an error because it's undefined. And actually also we get, if we try to do log of 0, we also get a domain error. So that's also going to be undefined. But we can pick any numbers that are really close to 0, like 0.1, 0.01, 0.00001. Remember, there's on that graph of a normal logarithm, we have basically an asymptote at 0. X equals 0, that's keeping us from getting over here where the negatives are, or even from touching 0. So on the domain for these, what we are concerned about is inside of here, when are we going to be greater than 0? Okay, now if we have two things like this, x times x plus 1, to figure out where that's greater than 0, we did a sign chart back in the day. If you remember that, x and x plus 1, we are going to have two important points where this part equals 0 and where this part equals 0. So at 0 and negative 1 are our important points. And what we do is we basically plug in a number like negative 2. We think about, if I plug in negative 2 here for x, well, I get a negative. If I plug in a negative 2 here for x, negative 2 plus 1, I get a negative. We plug in something in between these two, negative 1 and 0, so something like negative 1/2. If if I plug that in on the top here, this x, I get a negative. If I plug this in on the bottom, I would get a positive. Then I plug in some number over here, which could be any number really. Let's pick 10. So that gives me a positive on top and a positive on the bottom. And so what we're looking at is two negatives here means that that's a positive value. A negative and a positive, that's a negative value. Positive and positive, that gives us a positive value. And so if we're looking for where are we greater than 0, then we would say, oh, well, we're positive from negative infinity until we get to -1. And then we're positive again from 0 to infinity. Okay, look at the graph and see if that's really what you end up with. And so I'm looking at the graph real quick to see if that matches up. Oh yeah, it does. What's actually happening in your graph, remember that your calculator is not showing you the whole picture. It's actually it's basically got a couple asymptotes, vertical asymptotes. So it would continue getting closer and closer to -1 and closer to 0 without ever actually touching them. So that right there is our domain, and that's how we find it. Now let's look at this next example. And what's interesting here is if you think about the properties of logarithms, I have a plus sign here, and so what we did in one section is we combined these logarithms and we said, oh, well, that's log of x times x plus 1. And hang on, that's the same thing as example 6. So the message here is we do not want to combine these. Okay, you do not want to combine these because those combinations we have are only true if we're talking about positive values being plugged in. And so if we combine them, this weird thing happens and we end up getting more of a graph than we really should. So here's what you do to find the domain when I have two separate logarithms. You're going to find the domain of each of them. So the domain of log of x, the domain of log of x plus 1, and what happens is whatever is the most restrictive domain possible, that's going to be my domain. Let's think about what that means. Log of x, that domain is like a normal logarithm, like what I drew up in the top right corner, and so its domain is from 0 but not equal to 0, so we put a parentheses, from 0 to infinity. Okay, this logarithm with x plus 1, well, we need to think about when is x plus 1 going to be greater than 0, which is just going to be me solving that. So x is greater than -1. So to write that in interval notation, that's -1 comma infinity. One of these two domains is more restrictive than the other. Are there more values from 0 to infinity or from -1 to infinity? Well, there's more from -1 to infinity. You'd be starting on a number line. Here's -1, here's 0. We're going to infinity, and so we want to say, well, if this is our first one and this is our second one, we want where do they overlap, which is right here. So our domain for this function is going to be from 0 to infinity, and that's because that's the most restrictive, the more restrictive domain in this case. If you graph this, you'll see that it actually looks like our first one, just with part of the graph almost missing, is really what it looks like. So just go ahead and graph it and see for yourself. And if you graph them at the same time, actually it's really funny because you can't even tell the second one graphed because these graphs are connected. This one just has some negative values involved, because if I multiply a negative times a negative, I end up with the positive, so I don't end up with that domain error that I would have otherwise. We've got a few more equations to solve, and in this section it's going to say solve by the method of your choice, which means that you are free to solve this by graphing if you want to. Example 8, I'm going to show you how to do algebraically. And then example 9 we'll do graphing, because to me the book does this thing that's kind of magical. Like how do we know that we're supposed to do that? How does that really work out? So we're just going to graph it and do it that way. So example 8, do not be fooled here. Don't use the property that moves the 2 in front like this. Okay, you're going to be like, oh, that makes it so much faster. Don't do that. It's a trap. Stay away. Instead, let's remember that the natural log of x squared, or whatever we have, is the same thing as the log with a base of e. Okay, so we can rewrite this as e to the 4th equals x squared. Okay, and then we can say, oh, I just need to square root both sides to solve for x. And remember, if you, in an equation, take a square root, you personally need to put that plus or minus there. The square root of e to the 4th, that could be tricky, but think of it like the square root of x to the 4th. Isn't that x squared? So we don't need the square root that I was about to draw there, sorry. This would be plus or minus e squared, or we can go ahead and figure out what e squared is. Sounds like a good idea. Second ln squared 7.389, so x is positive or negative 7.389. So, and in this section it also says solve it by your method of choice and then check it with a different method. So in this particular case I would check it by graphing it personally. Example 9. Now when we set up to graph, I think it really helps out a lot if you go ahead and kind of simplify where you can. Like I can multiply both sides by 2 here and get e to the x plus e to the negative x equals 8. And then I'm going to go ahead and move the 8 over to the left side, and then I'm looking for the x-intercepts of this graph. Okay, that's what I'm looking for. So you go to y equals, and you type in e to the x plus e to the negative x. Make sure you close your parentheses on those e's if you have an older calculator that doesn't make it an exponent for you. We're going to graph this, make sure you have kind of a standard window, and then it actually looks like a parabola. And you would go second trace and go to 0. Remember that for the 0 menu, we want to go to the left of one of our zeros and press enter. Then we want to move to the right of one of our zeros. Then you can move closer to the 0 for it to guess, but you don't really have to. Whenever I do that, I get for my first answer here negative 2.063. I have a feeling that my other answer might be positive 2.063, but I'm not positive, and if I as a math teacher am not positive, then you should not be positive either. You should go and check it. So second trace, calculate, left bound, right bound. Yes, please guess for me. No, it is 2.063, so this is really a plus or minus case. And x equals 2.063. Okay, so the way the book does a problem like this, it's on example, let me see, example 2 actually, and so they are going to suggest that you multiply by a 2e to the x at the beginning. You end up with basically something that's quadratic in form, which makes sense since we saw a parabola, but it's just kind of a weird way of doing it in my opinion. So this is my recommended way on this. Now we're getting into the application part of things. So one thing that the book starts talking about here is orders of magnitude. One way to compare two quantities is by looking at their orders of magnitude. When we are asked to find how many orders of magnitude quantities differ by, we're basically being asked how many place value differences there are between the two. So for example, if I have a canary weighing 20 grams and a hen weighing 2 kilograms, and they want us to say how many orders of magnitude are those apart. One thing is it's helpful to change these to the same unit, like so 20 grams I'm going to leave alone. 2 kilograms, there's 1,000 grams in a kilogram, so this is 2,000 grams. How far apart are these, like place value wise? They're 2 apart. You see what I mean? Like 20 has a 1 and a tens, 2,000 has 1, tens, hundreds, thousands. This one has 2 more place values than 20 grams. So we would say that the let me think how to word it. It says determine how many orders of magnitude the quantities differ, and so we would say, well, they differ by 2. Okay, because this 2,000 grams has 2 more decimal places, basically, if you want to think about it. They're to the left of the decimal, not to the right, but there's 2 more decimal places than 20 grams. So let's do the same thing on this one. A penny, so that's 1 cent, in case you didn't know, and a $100 bill, so that's 100. Well, how far apart are these? This is 2 to the right, and this one is at 100. And actually, let's talk about a different way that might be easier. If you take these and put them over each other, 1,000 over 0.01, what do you get? I think I said 1,000, I meant 100. 100 over 0.01. What we get is that a $100 bill is 10,000 times greater than a penny. Okay, that's what that's telling us. How many zeros are there here? There are 4 zeros, so this is 4 orders of magnitude greater. Okay, 4 orders of magnitude greater, because what is 10,000? It's 10 to the 4th power. This has a lot to do with like scientific notation. If you have 2 really big or really little numbers that are in scientific notation, like let's say we have this number and we have this number, those are some pretty big numbers, but their order of magnitudes here, if you look, are 2 apart. Okay, because this is to the 7th power, 10 to the 7th power. This is 10 to the 5th power. So those are 2 orders of magnitude greater, or greater. Okay, so it's a little weird, but if you think about it for a little bit, hopefully it will make sense. So now we have some actual applications now to this. One of them being earthquake intensities. This is a formula we're going to use for earthquake intensities that allows us to calculate the magnitude of an earthquake on the Richter scale, which hopefully we've all heard of before. In this, A is the amplitude of the vertical ground motion at the receiving station in micrometers. T is the period of the associated seismic wave in seconds. B accounts for the weakening of the seismic wave with increasing distance from the epicenter of the earthquake. None of that really matters except, well, no, none of that is really going to make much of a difference at all in these problems. We are going to, in this example, say how many times more severe was the 1995 Kobe, Japan earthquake, which had a Richter rating of 7.2, than the 1994 Los Angeles earthquake, which had a Richter rating of 6.6. And so basically, if we label Japan as R1, and we say, well, this formula we have, which would have an A1 over T plus some B, we're saying that is equal to 7.2. And then we're also saying we have a second formula for our second earthquake, where we would have a second amplitude over, and we're going to call the T the same thing. Okay, it's the same T, it's the same B, it's just our A is different. And this time we get a Richter rating, I don't know if that's the way you would call that, but it sounds alliterative, so I'm going to go with it, of 6.6. Okay, and so we want to know how many times more severe the one in Japan was over the one in Los Angeles. So we are going to subtract these. We're going to subtract R1 minus R2, which means that we are saying log of A1 over T. I don't really need those parentheses around that. I'm sorry. I'm saying log of this minus log of the other. This is where I wanted my parentheses. This is R1 that I have in this parentheses. I'm going to subtract R2, which equals log of A2 over T plus B. Okay, so let's go ahead and put in R1 and R2. That's 7.2 minus 6.6. If I look here and distribute this negative, it's going to give me log of A1 over T. This plus B is going to cancel out with this B because it'll end up being a minus from distributing. So minus log of A2 over T. Then what I'm going to do is I'm going to say, well, 7.2 minus 6.6 is 0.6. And I'm going to combine these logarithms. I'm going to condense this into one thing. So if I do that, let's think about what I have. A1 over T is going to be over A2 over T. And however you want to think of it, if you want to think about it like this flips up, or if you want to think about it some other way, it's a T on top, not an I. These T's cancel out, leaving us with just A1 over A2. And so this is something now that I can solve. Okay, this is common logarithm, so it's got a base of 10. So we would say 10 to the 0.6 power equals A1 over A2. And that's actually what it's wanting, is how much greater in magnitude was the Japanese earthquake than the Los Angeles earthquake, which is this ratio A1 over A2. So we just want to find out what is 10 to the 0.6. 10 to the 0.6 is 3.981. Or the book would probably say about 4. About 4 times greater. And when we're talking about times greater, that makes sense that we would want to round a number like that to 4. Okay, we're saying it was about 4 times greater, which if you think about it, that's only 0.6 apart in the scale, and it was 4 times greater. So obviously we've got an exponential thing going on here. So that's earthquake intensities. Chemical acidity. So the book has some information about this if you need a little bit more information, but basically the acidity of a water-based solution is measured by the concentration of hydrogen ions in the solution, which is measured in moles per liter, and it's written as this at H plus in a bracket. The measure of acidity used we call pH, which is the opposite of the common log of the hydrogen ion concentration, which if you literally think about it, opposite is negative, common log of the hydrogen ion concentration. That's how we get this formula. So let's do this example. The pH of carbonated water is 3.9 and the pH of household ammonia is 11.9. Part A asks us what are their hydrogen ion concentrations. So we're going to use this negative log H plus thing that we've got going on. Okay, we're going to say that equals, for the first one, 3.9. And then we're going to solve this. I'd move the negative over and get negative 3.9 over here. And then this is log with a base of 10. So 10 to the negative 3.9 is my hydrogen ion concentration, which if we type that into our calculator, gives it to us in scientific notation, showing that this is a small number because it's to the negative 4. We know that's a decimal. Yeah, typically with scientific notation, we normally just rounded 2 decimals, so I just kind of automatically did it there, even though normally we want you to do more than that. So let's do this now for the second one. And I would understand if you wanted to skip a couple steps, because we just did this with just a different number, but we make the negative switch sides. We write this as 10 to the negative 11.9, and then we'll type it into the calculator. And if the first one was scientific notation, this one definitely will be, because it's to a higher negative power. So 1.26 times 10 to the negative 12. Okay, these are our two answers for A. These are the hydrogen ion concentrations. Wow, that was an awful circle on my part. Hopefully you wrote it down before that. And these are moles per liter for the units, in case you were wondering. Moles per liter. Both of those. Now let's do B. How many times greater is the hydrogen ion concentration of the carbonated water than that of the ammonia? So which one of these two numbers is bigger? It'd be the one with the smaller exponent, because it's negative exponent. So what we're going to do is we're going to take the 1.25 times 10 to the negative 4 and put that on top of 1.26 times 10 to the negative 12. Wow, those are really close numbers. Almost identical, in fact. We're going to call those close enough. And maybe if you actually... Oh, I rounded the first one wrong. Man, that should have been 2.6. I rounded the first one wrong. Those are identical numbers. Look at that. How nice. So really, 1.26 times 10 to the negative 4 over 1.26 times 10 to the negative 12. Guess what happens? Those 1.26's cancel, leaving me with 10 to the negative 4 over 10 to the negative 12, which we can actually figure out what that is without our calculator if we want to, because we subtract exponents to combine things when one's on top, one's on bottom. So that's negative 4 plus 12, which is 8, 10 to the 8. And so that's how many times greater the hydrogen ion concentration of the carbonated water is than that of the ammonia is. It's 10 to the 8th power times greater. And part C says, by how many orders of magnitude do the concentrations differ? We can get that answer actually one of two places. We just said it's 10 to the 8th times greater, which means that it's 8 orders of magnitude greater. Incidentally, I know this has worked on like 3 different problems, so I kind of feel good about it. If we had originally subtracted 11.9 and 3.9, we would have gotten 8. So I feel like that there must be some kind of connection there. I don't know if you're feeling it, but I'm feeling it. Let's look at our last example, Newton's law of cooling. We've got this formula right here, where we are going to, on the example I'm about to do, we're going to have to find K, but T of M is the temperature. Okay, what's going on is if we stick something like a cup of coffee that we have just heated up, if we stick that in something like an ice chest, then the air around the coffee is going to cool the coffee until it gets as close to as possible to the temperature that is inside the cooler. And so this formula that we have is going to model that. So T of M, the temperature of the surrounding medium. The surrounding medium a lot of times is going to be air, or if you like dropped something in water, cold water, like your medium would be water. T of 0 is the initial temperature of the object, or T of O, depending on what you want to call it. T is the amount of time that it's been going on. So, by the way, I put example -3 because I feel like this has gone on so long that we've actually gone around in time to negative numbers. Anyway, a cup of coffee has cooled from 92 degrees Celsius to 50 degrees Celsius after 12 minutes in a room at 22 degrees Celsius. How long will the cup take to cool to 30 degrees Celsius? So they're giving us an initial scenario, and the coffee was 92 degrees when it started. So T of O is 92. And I wrote out degrees Celsius in the problem out of laziness to try to find the degree symbol. So there's degrees Celsius. 50 degrees Celsius is what it cools to after 12 minutes. So our T right now is going to be 12 minutes. And our big T of T right now is going to be 50. Okay, because we've gone from 92 degrees Celsius in 12 minutes, we've gone to 50 degrees Celsius. They tell us the room is 22 degrees Celsius, so that's T of M. We're going to use this all to find K, and then we'll be able to plug it all back in and figure out how long it's going to take for the cup to cool to 30 degrees Celsius. So T of T is going to be 50 degrees. T of M is 22. T of 0 is 92. Minus T of M is 22. Times e to the negative. We're trying to find K. And then this is taking 12 minutes. So let's do this math. I can do 92 minus 22 because that's 70. I can subtract the 22 degrees over to the left side. Sounds like a good idea. So that's going to be 28 degrees equals 70 degrees times e to the, let's do this, negative 12k. Looks a little nicer to me. Now we can divide by 70 on both sides. And 28 over 70, I mean, we could write it as a decimal because that's actually a really nice decimal. That's 0.4. So that would actually also be a really nice fraction, so whatever. Now, because I have an e here, it'd be great if I took the natural log of both sides. So that natural log of e goes away, giving me the natural log of, this would be a good time to use something like 0.4 instead of just saying 0.4 equals negative 12k. So we divide by negative 12, and that's going to give us our k. Natural log of 0.4 divided by negative 12 is 0.07636. I feel like we should have a lot of decimals because we're about to plug this back in now. Now for, like, that was all to find K. We want to know now how long it will take the cup to cool to 30 degrees Celsius. So our T of T now is 30 degrees. That's how much we want it to get to. Our, now I don't even remember what the formula is. T of M, the medium that we're in, is the same. It's still a room of 22 degrees, at 22 degrees. Plus our initial temperature is the same. This is the same. But we're not going to plug in T. We are instead going to put in K. And if possible, maybe I can work it out to where I can use my second answer button in my calculator here. All right, let's solve this. Again, this is 70. We'd subtract 22 over here and get 8 degrees equals 70 degrees times E. I didn't put the E there. There's an E there. Don't forget the E. E is very important. Negative 0.7636 T. Divide by 70 on both sides. 8 divided by 70. Now that's not at all a nice decimal, so I'm going to leave it as 4 over 35. So 4 over 35 equals e to the negative 0.7636t. I think I just ruined my plan to use the second answer button, but we take the natural log of both sides. So we're saying that the natural log of 4 over 35 equals the natural log of e to the negative 0.7636t. This ln of e goes away. So we're really just going to divide this natural log of 4 over 35 by negative 0.7636. So natural log of 4 divided by 35 divided by negative 0.7636 gives me a negative number, negative 63.54, which seems a little bit weird that it would give me a negative number. But I'm gonna go with it for now. So that's my answer right there. So we now have our K, and we want to plug in everything from the original problem except for our original time. And now we're going to plug in, we want 30 degrees Celsius, so that's T of T, so it's going to go on the left side, equals T of M is still 22 degrees. Inside our parentheses, we still have 92 degrees minus 22 degrees. And now, instead of having what we had before, we're going to have negative K, which we said was 0.07636 times T. We're trying to figure out how long is it going to take for this to actually occur, so we're solving for T. So let's subtract 22 degrees. Eight degrees equals 92 minus 22 is still 70. And we're going to divide by 70 and get 8 over 70 is not a nice decimal, so and it doesn't have a 5. If I reduce it, I get 4 over 35. Is e to the negative 0.07636t. Now it's time to take the natural log of each side. That natural log of e goes away, so really we're doing the natural log of 4 over 35 divided by negative 0.07636. Type that into your calculator, and you should get 28.41 minutes. So it's going to take about 28.5 minutes for the coffee to cool to 30 degrees.